Okay, ladies and gentlemen, we're going to do the best we can to get started with this circular motion. So you did a lab with an object spinning over your heads, and your job was to graph the lab, okay? And so I had you doing two graphs. I had you do a graph of velocity versus radius, and I had you do a graph of velocity squared versus radius. Okay, so in those two graphs, the most important thing is the slope of the line and what that actually tells you. Unfortunately, we don't get the best data. Okay, so the data on the velocity versus radius graph should not have been a straight line, but you guys are very used to trying to make it linear. Okay, and you did that. Okay. When you do that, and we plug that into an equation of a line, okay, what you should see is the y-axis is the velocity, and m is the slope, and the x-axis is radius, okay? The plus b shouldn't matter. What you really need to look at here are what would be the units of the slope, okay? So if I solve this for the slope comes out to be the velocity divided by the radius. That's our slope. And if we consider units of that, okay, units of velocity are meters per second, units of radius are meters. So what would happen is the meters would cancel out, and we would get 1 over a second. And for right now, that's not a very useful unit. So you come over to the velocity squared graph, and there's got to be a reason why I'm telling you to do velocity squared, okay? And for some reason that's probably going to come out to be more exact. But you should have gotten a better linear line with this graph, okay? Now, it doesn't always come out to be great because, again, okay, we need to be better at doing laps. But again, we are interested in the equation of the line, y equals mx plus b. Well, the y is velocity squared. The m, we still don't know what that is, but it's the slope of our line. And the x, again, is the radius. And we should be able to logic away the b, because if you have zero velocity, okay, you would have a zero radius. Now, in this, then, the velocity squared part, so I should back up. Again, I'm interested in what is the slope, okay? So if you look at this, the velocity squared divided by the radius, and you look at this in terms of the units, okay? Well, velocity is meters per second, and then that's squared, so that would be meters squared per second squared, all over a meter. Well, now one of those meters cancels that out, and our unit of slope comes out to be meters per second squared. That is our slope units. Well, that meters per second squared should be a very common unit to you. Okay, and what that common unit what you should recognize that to be is that's the unit of acceleration. Okay, and since that is the unit of acceleration, what is happening here when this object is spinning around this circle, okay, it is actually accelerating. But wait, how can it be accelerating if we are moving at constant velocity? Because you should have been very specific with this in terms of it's moving at constant velocity. And it actually goes back to the definition of what a vector is. Okay? And acceleration, we know, is a vector quantity. And vectors have magnitude and direction. And it's the direction part of this that makes this acceleration. Okay? So we go back and we look at the acceleration equation. Acceleration is v final minus v initial divided by time. Okay? Well, if you think in terms of a scalar number, okay, this acceleration should be 0 if our velocity is constant. So if velocity is constant, then we would think, well, if v initial is 10 meters per second and v final is 10 meters per second, then looking at this and going up here, I could probably logic out that, hey, that should be 0. But it's not 0 if you consider the fact that we have to deal with direction. Okay? So, we're going to look at this in terms of this whole idea of direction. So, on here, what I have is a circle, okay? And we're going to assume that this circle is rotating, okay? And I am going to be interested in specific points on this circle, okay? So I'm going to make points around this circle, and those are going to be points that actually have velocity. Now, what I'm going to do here is I'm going to remove the actual circle part of this, so I'm going to get rid of that. Okay? And so these points that I just made were points that were on that circle, okay? So if and you'll notice that they all have vectors. If I call this V initial, then that's my initial velocity. This vector right here then becomes V final. Notice that there is a change in direction. And that's what makes this have an acceleration. Even though these two velocities, this one and this one, might have the same magnitude, they might both be 2 meters per second as their velocity. It's the change in direction that is the issue. And then this goes back into our addition of vectors, where how do I actually add vectors? And if you think about that, and remember that, we add vectors head to tail. Okay, so with these two vectors, if I go follow my rules of vector addition and I add them head to tail, okay, I'm going to get rid of those. Take this vector and I'm going to add it to this vector. Now, you have to remember that this acceleration is v final minus v initial over time, which means I have to take this vector here and I have to make it go in the exact same direction or exact same magnitude but opposite direction. So I have to flip the vector when I do that. And now, when I take V initial and V final, and I subtract them, there is right here a change in velocity. Okay? And that happens all the way along here. So if I call this vector V initial and this vector V final, okay, if I take them and add them together, okay, knowing that, again, I have to flip them because that's my definition. Then again, right here, there is a change in velocity. Okay, and just to show that one more time, I'll use this vector and this vector. If I add them together, and again, remember, I'm subtracting, so I know right now that I'm really putting two heads together, and I can't do that. It's just to flip them in this video takes too long. Okay, so I'm flipping it like this. And then notice this right here, again, is my change in velocity. So, even though we have constant velocity, when you add them as vectors, you get a change in velocity. Okay? And that's the change in velocity is why this is acceleration. Okay? Now, here is the other really interesting point. Notice where all of these changes in velocities are pointing. These change of velocities all point to the center of the circle, which means this acceleration actually points in. This acceleration then is actually called centripetal acceleration. Okay? We are going to use the letter A sub C for this acceleration. And it is acceleration due to uniform circular motion. Okay? Essentially, that's meaning that the velocity is constant. The velocity is constant, but we have acceleration because of what I just showed. So right here, the velocity is constant, but it's changing directions. And here's the other important thing. That direction is always towards the center of the circle. So if you watch this little animation right here, okay, you will see the blue vectors are the constant velocity, and you'll notice that they're not changing size. And it's hard to see here, but there is a green vector that is the acceleration vector that's pointing towards the center of the circle. It's overcome by a red vector, okay? But that acceleration is towards the center of the circle. So, our equation then for centripetal acceleration essentially comes from that graph. It is v squared all over r. This equation is note card worthy and should be placed onto your note cards. Okay? You can do that as you go. If we look at the units of this, okay, you would have a meter squared per second squared all over a meter. And the meters would cancel one. So that gives you your acceleration units of meters per second squared. It's a fairly simple plug and chug equation right now. And that's what you're going to be doing for homework is you will basically be plugging and chugging that out. Now, if we have a centripetal acceleration, how does that apply to Newton's second law? Newton's second law says force equals ma. Well, what if that acceleration is centripetal acceleration, which is mv, which is v squared over r. Then I can plug this into Newton's second law, and that would become force equals mv squared over r. And this then becomes centripetal force. Okay, now, notice the language here. It is centripetal force, not centrifugal. There is a difference in those two terms. Okay, but centripetal force is a center-seeking force, and it is actually the force that causes objects to move in a circle. Okay? And the direction of this force is also towards the center of the circle. That's why if you go to this picture, these red vectors that are in here, those red vectors, okay, are the centripetal force. So the centripetal force and the centripetal acceleration are the same. Okay? This is the force that must be applied to keep an object moving in a circle. Okay? Now I'm going to go down to this. This force, this is huge. the centripetal force that causes an object must be supplied physically. And I'll show this in class on Wednesday, but you actually have to supply that force physically. Okay? And by physically, you have to put an object on a string. Okay? You did that yesterday in the lab. Okay? You were applying a force to the rubber stoppers with the string. Our Earth rotates around the sun because of the force due to gravity. And a car will go around a corner because of the force due to friction. Okay? So because of this, centripetal force is really a net force in every case. So we're not going to get into this today, but when we start applying this force, which is really where the fun begins with this, is the sum of our forces is going to equal our net force, which in all of our last problems we have been putting as MA. Well, if an object is going around a circle, that net force is really the centripetal force, so that becomes mv squared over r. And we will do more of that type of thing on Wednesday, okay? So just be aware that the centripetal force is really the net force in every case. So just to show this, okay, if you look at motion, one of the things that we think about is, well, how do you go around a corner in your car? Well, this is a ball that is moving in a straight line. If there's no force applied to the ball, it's going to continue moving in a straight line. That's essentially Newton's first law. Objects in motion stay in motion. Okay? In order to get that ball to move in a circle, okay, you have to apply a force. So this is the same exact ball moving in the same exact straight line, except now there's an outside force that's being applied to it. Okay, now you could consider this as being you in a car. Okay, and in your car, the door of your car would be applying a force that causes you to go in a circle. Okay, here's another example of that where you kind of have to watch this, but there is a tape right there. Okay. And this is a top view of that tape, and this is the side view. And this tape is going in a straight line. Right here, you will see that it is moving in a straight line. And if the window of your car is open, okay, that tape would simply continue to move in a straight line. But if you shut the door, then that can't move in a straight line, and it follows you around the corner. This is something we're going to have to talk about a little bit in class, and I will review that a little bit. But essentially, we're going to use this to do a couple of our problems, okay? And the type of problems that you have assigned for today are very straightforward. You are going to use the equation AC equals V squared over R, or you're going to use FC equals MV squared over R. Okay, these are plug and chug, so you shouldn't really have a hard time doing them. Okay, some of the simplest equations we have done for a while. So in this problem, you have a 900 kilogram car that's moving at 10 meters per second around a corner. That corner has a radius of 25 meters. We want to determine the acceleration. Well, that's fairly straightforward. The acceleration is v squared over r, so 10 meters per second quantity squared over the radius, 25 meters. And if you plug and chug that math into your calculator, you come out with 100 divided by 25, which gives you 4. And then your units would be meters per second squared. So it's really just plug and chug. So then to find the centripetal force, that is MAC, okay, since I've already calculated that, okay, right here, we're good. I can just plug that in. So M's, the centripetal force is going to be 900 kilograms times the 4 meters per second squared. So the centripetal force is going to come out to be 3,600 newtons. Okay? Your assignment that you'll be doing is just plug and chug.